Hi everyone, Mr. Lee here. In this video, we are going to go over a very special type of collision. It is called the explosion. Alright, yeah, explosion. Now, the title of the collision, explosion, it might sound exciting, but believe it or not, we've already covered this type of problem before. Now let's take a quick look. Now, for an explosion type of problem, we'll start off with the base model. Let's say we have two clay spheres. We have a red sphere right there, and we have a blue sphere right there. Okay, and we put right in the middle, right there, right in the middle, like a tiny bit of explosive, so that when we trigger that explosive, the two spheres they fly apart. Oops, that should be blue. The two spheres, they fly apart. So the blue sphere will fly to the left, and the red sphere, it'll fly, the red sphere will fly to the left, and the blue sphere will fly to the right, and there's a tiny bit of explosion right there. Okay, so this is a type of a explosion problem, and unlike a lot of things in physics where the word that we use in a day-to-day language compared to like the physics definition of it, where usually it's different, explosions, not different. It's exactly what you think it is. It is a object that comes apart, an explosion. And if we take a look here, because we want to view this through the lines of, or the eyes of momentum, we can say that the initial momentum is equal to the final momentum. And this is because there are no outside forces. Now, I keep on bringing this up. This is a very big idea. If there's an outside force to the system, then we have this thing called an impulse, and an impulse is the change in momentum. And right now, we're saying there is no change in momentum. So your initial momentum is equal to your final momentum. So how do we come up with this equation for an explosion? Well, it's simple. We just take a look at the momentum of the system. So in this case, even though we can view this as just one object, right, to make our lives easier, I'm going to say this is actually two objects that's combined into one. And whenever we have the combination of objects, we use the parentheses. So we say that the mass of the red ball plus the mass of the blue ball, or the blue, clay piece, times the initial velocity is equal to the mass of the red ball times the velocity of the red ball final, plus the mass of the blue sphere times the velocity of the blue sphere final. Okay, and so the way that we can look at it is this parentheses right there, the parentheses, it tells us that there are a combined set of objects, right? It's combined. So the parentheses shows us that it's combined, and it is just one solid object. And the velocity is the shared velocity. And the reason why I say that is because technically we could distribute this initial velocity so that it looks like this, plus mb/v/o is equal to mr/vrf plus mb/v/bf. So we can say that if we were to distribute the velocity factor across. But to make things simple, I like to always use the parentheses method just so that we can see that it is two objects combined into one. Okay, and I'll write that out again because we're going to be using that again. Okay, so what this tells us is that the forward momentum of this blue ball is equal to the backwards momentum of this red sphere. Okay, and if we take a look at this equation down here that I wrote, this equation, this is an equation that we've already discovered. In fact, if we swap the location of the left-hand side of the equation and the right-hand side of the equation, what we would get is, let's see, I'll write it out, m plus mb/v/b is equal to mr plus mb, and we'll say this is v final. Okay, so we have the momentum of the red sphere plus the momentum of the blue sphere is equal to the final momentum of the combined spheres. So if I were to draw out this equation, it would look something like this. We have a red sphere with some form of velocity, and this mb/v/b, that is a blue sphere with some form of velocity, and after some collision happens, remember what the parentheses means. The parentheses mean that we have two objects that have been combined into one. Okay, and they are both moving with some velocity. We don't know what it is, right? And so this is a inelastic collision. And so what that tells us is that an explosion is a reverse inelastic collision. Cool stuff. And all the properties of a inelastic collision still apply. Okay, and let's go over those because those are important. The first one is momentum is conserved. Momentum is conserved. Second one, energy is not conserved. More specifically, kinetic energy is not conserved. Okay? Okay. So here we have the equation for a explosion type of problem. Now, of course, we can expand this if there are more objects. So for example, let's do 3 objects. Let's do, we have this, like, let's say like a jawbreaker, like a hard candy, right? And that hard candy has 3 different pieces. We have piece 1, piece 2, and piece 3. And once again, we're going to put a tiny little bit of explosive right in the middle of the candy. Okay, and then the candy explodes. So we have 1 flying this way, pew! We have 2 flying this way, pew! And we have 3 flying this way, pew! Right? So these are all zipping around, almost like a grenade or like an explosion. And so in this case, our formula will look the same. We'll say that P initial is equal to P final. And I don't want to spend the time to really write out the equation, but how we could, write this equation out is that we have m1 plus m2 plus m3 times the initial velocity is equal to momentum of 1 plus the momentum of 2 plus the momentum of 3, because there are 3 different objects. Okay, and from here we can expand this out even more using the momentum formula, which is P equals mv. All right, and so we can do this for a infinite amount of objects. Now let me tell you why this is particularly amazing. We went from like a theoretical point, and let's zoom out a little bit, right? So like a real world situation. Sometimes if you go on YouTube, there's like these YouTubers that do some really fun, cool looking things. And one of them that I've seen recently is a watermelon. Yeah. So you would get this watermelon. Wow, that's a pretty good watermelon. Right? Let's see if I could. Yeah, that's not too shabby, right? All right, so we have a watermelon, and what they would do is they would drill a hole at the top of the watermelon, and they would put a tiny little explosive in the middle of the watermelon. Okay, and then they would detonate the watermelon. And after they detonate the watermelon, oh man, it's like fantastic. So we have like pieces of watermelon flying everywhere, right? And the pieces are exploding, and because these are YouTubers and they want all those awesome views, they do this in slow motion. And in slow motion, you can see like the insides of the watermelon, just all the watermelon juices and the watermelon pulp just flying everywhere. Now, here's what's really, really cool about this whole situation. Not only is it cool to watch watermelons explode, but the cool thing is, right? Well, I think it's pretty cool. Is that if we were to find the momentum of every single piece of watermelon that is flying away, exploding away from the original, where the watermelon originally was, if you add them all up together, the momentum would add up to be 0. And that's because, in the YouTube videos, right, the watermelon is just like there, it's not moving, and so the initial momentum of the watermelon is 0, and after it explodes, if you add up the momentum of every single piece of watermelon that is flying, and you were to add them up, you would get 0. And that's because the conservation of momentum still applies. Now, we can expand this to even great, like, to our universe. Okay, so one really cool thing about our universe right now is we are currently under this theory of the Big Bang, right? The Big Bang theory. So what the Big Bang says, well, we don't know like how the Big Bang started, but what we do know is currently our universe, so I'm going to draw space, right? Oh, okay, here's space, and this is my universe pen. So we have this universe, and this universe, the outer edges of the universe, is currently expanding, right? Oh, don't do that. Yeah, this outer edges of the universe, let's see, let's do this in red. The outer edges of the universe are currently expanding outwards. And you might be wondering, well, where are we, Mr. Lee? Where are we? Well, I'll show you exactly where we are. Okay, so the outer edges of the universe are expanding, and if we were to zoom in, our Earth is like right there. Boop. I'm joking. That's not where we are. I don't know where we are in the universe. We're somewhere in the universe. But what we do know is that the universe is currently expanding. And this idea is very important because if we apply the laws of conservation of momentum and conservation of energy, if the universe is expanding, it's because something caused it to expand. There is a explosion. And so what we can say is that if we were to find the momentum of every single thing in our universe, every single planet, every single star, every single dust, every single thing in our universe, and we were to add them all up, we will find that the momentum could be traced to this whatever was in the center of our universe. And the momentum added all up would be the momentum of the beginning of our universe's existence. Isn't that wild? Yeah, like a equation that we can use to see, I don't know, like a watermelon exploding is the same equation that we can use for our universe exploding. Fantastic. All right, so before I end this video on that conceptual note, I do want to go over a couple of things about the variables. So if we have two objects that are of different masses, so let's say we have mass 1 and we have mass 2, right? Mass 2 is really, really big. And let's say it's an explosion type of problem. And the question will be, like, if the two objects are exploding, which object is moving faster? Okay. Now, this is what we know. We know that momentum of 1 is equal to the momentum of 2. Okay, because momentum is conserved. So these two objects have the same momentum. And if we take a look at the equation, mv is equal to mv, we know that because mass 1 is so small that as it's exploding, the velocity is huge. The velocity is ginormous compared to mass 2, where the mass is big. Therefore, it's going to be flying away slower. So we can say that the velocity of 1 is going to be greater than the velocity of 2, and that's because the mass of 1 is less than the mass of 2. However, the momentum of 1 is equal to the momentum of 2. Okay, so that's a concept type of problem that you might come across. Another one that you might come across is, let's say, we have a scenario where we have a object, right, object 1, and we have object 2, and both of these objects have an initial momentum, so they're both moving forward. Now, up until this point, like all the examples that we went over, the initial momentum was 0. Okay, but in this case, let's say the two objects that are moving together, their momentum is not 0, so they actually have a initial momentum of something. We don't know what it is, but we'll just call it momentum 1, or I guess momentum A. All right, so it has an initial momentum, and so after it explodes, like it explodes, and we have these two objects that are flying. Okay, we can say this: if this object is flying to the left, the object that is flying to the right, the velocity, this will be usually greater than the one that's flying to the left. And that's because the initial system had a forward momentum. So when we add up the momentum of both of these objects, it has to carry a forward momentum. So that means the momentum of 2 has to be greater than the momentum of 1. Okay? And a different kind of scenario, right? Same kind of scenario here where they're both moving forward, but after the explosion, we have both objects that are flying forward. Okay, now this can also happen because if we add up both of these momentum, they are both in a positive direction. Now this can only happen in like very special circumstance, and so you won't always see this type of problem happen. Chances are you'll see something more like this where they're both flying off in opposite directions. Okay, so I just wanted to cover both of those ideas. So the big idea between here is how can we mess around with the variables to see which one has the greater velocity based on the mass. And this one is the idea of if the system has an initial momentum, even after the explosion, the system's momentum must be conserved. So if it's moving to the right in the beginning, after the explosion, the total momentum will still add up to be positive, and vice versa. If it was originally moving to the left or the negative direction in the beginning, after the explosion, the total system's momentum will add up to be negative overall. All right, well, that is it for explosion. Next time, we're going to take a deeper dive into this whole idea of systems and the momentum of a system. And until then, I'll see you later. Bye-bye.